Hey, welcome. Ever stop and think about how scientists and engineers can talk about, well, everything in the physical world? From a single drop of rain to a giant industrial reactor, they use the exact same language. It's this universal language for describing matter. And today, we're going to learn how to speak it.
So let's put this to the test. Imagine you're making vinegar, and I don't mean for a salad dressing. I'm talking 10,000 gallons of it for a factory. A splash of this or a cup of that from your kitchen recipe? Yeah, that's not going to cut it. You need absolute, unwavering precision. So, how on earth would you write that recipe? That's the puzzle we're here to solve.
Okay, so first things first. Before we can even think about mixing ingredients, we have to get a handle on the most basic question of all. How much of this stuff do we actually have? This right here is the absolute foundation of our entire language.
The first, and honestly the most fundamental tool in our kit is mass. Put simply, it's just the amount of stuff that makes up an object. It doesn't matter if we're talking about a few grams of a chemical or hundreds of kilograms of water. Mass is always our starting point.
Now, right alongside mass, we've got volume. This isn't about how much stuff there is, but about how much space it takes up. You know, like 25 milliliters of liquid or a 10,000-gallon tank. Volume is all about the physical space our substance fills.
So, we have mass and we have volume. How do they connect? Well, they're linked by this really crucial idea called density. Think of density as the bridge between them. It's the mass that's packed into a certain amount of volume. It's the perfect translator that lets us go back and forth between the amount of stuff and the space it occupies.
And here's where we have to be super careful. The units are everything. I mean it. When you're converting between mass and volume, you have to track your grams, your milliliters, your kilograms. As our source material points out, writing down your units every single time is the best way to make sure you don't make mistakes. In this game, precision is king.
Okay, so speaking of density, that leads us to this other idea called specific gravity. It's basically just the density of something compared to a reference, which is usually water. Now, since it's a ratio of two densities, it kind of seems like the unit should just cancel out, right? Making it a nice, clean, unitless number. Well, is it really? And surprise! The answer is not quite. While the number itself doesn't have units attached, it's kind of secretly carrying the units of whatever you compared it to. So the specific gravity of nitric acid is 1.51, but that number means something totally different depending on whether your original densities were in grams per centimeter cubed or pounds per foot cubed. Now, the really cool thing about specific gravity, it's a super fast way to know if something will float. If the number is less than 1, it floats in water. More than 1, it sinks. Simple as that. All right, so density and specific gravity are great for understanding the big picture properties of our stuff. But what about chemical reactions? For that, we have to go way, way deeper. We need a way to count the individual atoms and molecules. So how in the world do you count something that's literally uncountable? Well, you use a very clever concept called the mole. So what is a mole, officially? Well, it's the standard international unit for the amount of a substance. It's not a measure of weight or space, it's a measure of quantity. It's a specific set number of particles, whether those particles are atoms or whole molecules. And just what is that magic number? It's Avogadro's number, and it is absolutely mind-bogglingly huge. That's 602 sextillion, 200 quintillion particles. I mean, just wow. So why is it so big? It has to be, because atoms are so incredibly tiny. We could never count them one by one, so we have to count them in these giant batches called moles.
Honestly, the best way to wrap your head around it is this. A mole is just a chemist's dozen. You know, when a baker talks about a dozen eggs, you know they mean 12. Well, when a chemist talks about a mole of water, they mean 6.022 times 10 to the 23rd molecules. It's just a convenient shorthand for counting on an atomic scale.
So that's great. But how do we connect this gigantic count of atoms to something we can actually, weigh on a scale in a lab? The answer is molecular weight. It's the bridge that connects the two worlds. As you can see here, 1 mole of any substance will have a mass that's equal to its molecular weight in grams. 8 kilomole, that's its molecular weight in kilograms. It's this beautiful, direct link between the invisible world of atoms and the physical world we can measure.
All right, we now have the tools to measure how much. So let's get back to our vinegar factory. We're ready for the next step, defining the exact composition of our mix. What percentage is the acetic acid and what percentage is the water? We need to be precise.
And it turns out there are two main ways we can look at this. The first is mass fraction.
This answers the question, what percentage of the total weight comes from this ingredient? The second is mole fraction, which answers a totally different question. What percentage of the actual molecules in here are this ingredient? Both are super useful, but they tell very different stories about our mixture.
Let's break down our vinegar recipe. We have 10 kilograms of acetic acid and 90 kilograms of water. So the mass fractions? Super simple. 10% acid, 90% water. But watch what happens when we convert to moles. Because water molecules are so much lighter than acetic acid molecules, that 90 kilograms of water contains way more individual molecules. So when you look at it by mole fraction, our mixture is actually almost 97% water molecules. See? Two totally different perspectives.
Now, of course, there are other ways to talk about a mixture. You'll probably run into terms like concentration, molarity, or molality. They all basically describe how much of one thing is dissolved in another. You see these pop up all the time, especially in chemistry and biology.
We are so close. We know how much of each ingredient we have, and we know their exact proportions in the mix. But there are two final, absolutely critical pieces we need for a perfect, repeatable recipe: the conditions our mixture is actually in.
First up, temperature. Now, we're all used to relative scales like Celsius and Fahrenheit, which are based on reference points like water freezing. But in science, we often have to use absolute scales, like Kelvin. Kelvin starts at absolute zero, the coldest it can possibly get anywhere in the universe. And why does this matter? Because temperature controls everything, from how fast a reaction happens to whether our vinegar is a liquid, a solid, or a gas. For a lot of calculations, using an absolute scale is non-negotiable.
And finally, our last piece of the puzzle: pressure. That's just the force that's being applied over a certain area. And just like with temperature, we can measure it relative to the atmosphere around us, that's called gauge pressure, or we can measure it in absolute terms. And for so many scientific processes, you have to know the absolute pressure. I mean, think about it. If you're trying to contain a gas or boil a liquid at a very specific temperature, pressure is the one variable you absolutely cannot ignore. It's vital for safety and for making sure the recipe even works at all. And there you have it: mass, volume, density, moles, fractions, temperature, and pressure. This is the universal language of the physical world. It's the language that allows us to design everything from life-saving medicines to rockets that travel to other planets. So the only question left is, now that you know the language, what will you build?